One of the problems which have not come to us and we did not realize what to do with it is being that this material is in a solid state of matter. What does it mean? If we choose the copper, this is the wire. You have to remember, I'm not Picasso, so you got to live with what I do. So this is your wire. This is what we have. All we did, we put current through it that by the vibration of the electrons in this wire, we managed to put some energy as current in. Oh, we go back. Doesn't matter. We managed to put energy in, and what we did, it was very easy. We got something out, but what it was irrelevant. Because we knew we lose some energy along the line, and we always considered some losses. As we know, the losses down the copper line became the dispute between Tesla and Edison. Edison tried to transfer the DC with the huge losses that every 10 kilometers or so he had to put a power station to boost the energy. Tesla came with phasing it using the vibration. So in so many ways, so what we done up to now, we relied on the vibration of electron, which is very, very minimal. It's absolutely insignificant compared to the total energy. But that's all we knew. Going into understanding the plasma, as you've been through with us over the past year, 2 years, and the other teaching, you came to understand we went through a specific process where we do not need the copper wire in a matter state. We start making a more efficient use of this copper. How do you make it more efficient? In the present physics, in the present time of electronics, they tell you and they talk about superconductors and super resistors and everything super that can carry the energy with a minimum loss from A to B. So what happened? Our dream has been to create the minimum loss between these two, using and understanding only the vibration of the electron. But in the current time, in the past few years, and as we put, for example, the first signs of creation of superconductors on the internet as a Coca-Cola bottle some 10 years ago, we start raising interest in other people, how this thing works and what it is. So what we did, we still took the same copper, but we brought the superconductivity from this wire itself, not from outside. If you go and buy nanomaterial, you want to coat this wire with nanomaterial, you have to buy a nanomaterial separate, glue it, or do something else that it can create, or have a layer of nanolayer on it. The way I set up to do it, being a nuclear physicist, understanding in the nuclear structure, we can separate the atoms in a much easier way than what we've been told. So I initially used caustic, and then electric currents, and then other bits over time. So what we've done, if you look here, if they were the atoms connected to each other in the structure of the copper, like this, we allow them to be where they are, but we created a very, very special condition. Very, very special condition. And that special condition was that in a matter state, if you heat the wire, it will melt. If you heat the molten metal further, it will evaporate. The trick was to create a condition that you don't melt the wire, and the minute the evaporation as a gas of copper created, you can reduce it, that it can pull itself back. That was the trick. To create a nanomaterial in a different shape or form, which was allowing to create nano layers of the metal itself, of the copper itself. So what happens now? We managed to bring them back to be in touch with the copper, but still you see separated according to the gravitational magnetic field. Understanding that even in a matter state, each structure has its own, what you call, gravitational magnetic field. It's like Earth. It has a south pole entry and it has a north pole exit. Every single cell in this structure is the same. Every nanomaterial is the same. And when you do this, you find out here, due to a stronger gravitational magnetic field and less magnetical field, which is repulsion, the matter stays more compact. If you reduce the gravitational field strength in respect to the copper and increase the magnetical, which is repulsion, then you get exactly the same state as you get with two magnets. If you have a north pole and a south pole, or if you have a north pole and a north pole, or south pole and a south pole. A plasma behaves exactly like a magnet. It has polarity. It's the sun. If you look at one of these, you see the sun. You see the earth. Earth is a plasma too. So what it is, the gravitational magnetic field between the two creates a gap, a distance, where they can coexist with no problem. The gravitational magnetic field between the Earth and the Sun dictates the position of the Earth in respect to the Sun. It's the same with your nano layers on top. Because don't forget, the bound and the binding of gravitational magnetic field on a wire is stronger, so the nanomaterial behaves as a satellite. And what happens is that now you have put this wire here. When you give it the right heat and the right condition, you create nano layers. But if you look, the nano layers are positioned magnetic gravitationally in respect to each other, where magnetical field is bigger, stronger, gravitational less compared to before. So now what you have is you have a spectrum here of nanomaterial flow. Superconductivity, where there is the orange line, because now you have less resistance to compact, so the material behaves as a superconductor. So what it was to heat the material high enough in a very short span, very rapid, that it releases itself from the matter state solid to nano state solid. And the proof of that was that we could see, if you look from above, a black line. The black line was the indication of nanomaterial, because on the top surface of these nano layers, when you look on the top, being black means they absorb every radiation which comes to the wire. If you look, this is a nano-coated material and it's totally black. Every single wire is black, which means it's totally nano-layered. Now, this was half of the problem.